Hello everyone, and welcome back to video lecture series on computer architecture. This is video lecture number 3. My name is Dr. Prashant Bachanna. So in the today's lecture, we shall be learning these following topics, that is the memory hierarchy design. So in this, we'll see the introduction to the memory hierarchy design, then important principle of locality, then spatial locality, then we'll see the memory wall problem, then how to design the memory, then the performance gap and the different parameters of the caches will be discussed. So in the memory hierarchy design, there's a principle which is called as a principle of locality. So this is the tendency of a processor to access the same set of memory locations repeatedly over a short period of time. So this is the principle in which the memories are designed. That is principle of locality, in which the instructions executed will be stored in the nearby address locations, address locations which are near to each other. So in the principle of locality, so it's a tendency of the processor to access the same memory set of locations repeatedly over a short period of time. So this you can see in the this diagram. As it's a secondary memory as input output devices. This is the main memory and the CPU. So here every time the processor will try to access locations which are near to each other. So this concept is called as principle of locality. So there are you can take an example of this. This is an example of principle of locality. So there are basically two types of locality. That is temporal locality, which will refers to the tendency of the program to access memory locations that were recently accessed. That is, in the simple terms, it is tend to reuse the data that have been used recently. That is temporary locality. And there is a special locality. So in this, it is a tendency for a program to access memory locations that are close to together in a memory. So this is because the data is often stored in the memory so that it is accessible. It will access the nearby locations. So that is organizing the memory system into the hierarchy with the fast but the smaller memory closer to the processor is the challenge. That is, in the memory hierarchy, we have to place the memories, the fastest memories which are close to each other. So we can see an example of this memory, example of this principle of locality, wherein we have taken an example. This is a program written inside the processor for the working of the memory. That is, for I equal to 0, I is less than 1, I plus plus, and for j equal to 0, this one. So here, if you see the loop order, the outer loop is the outer loop iterates only once. That is, for the value of I is less than 1. So this suggests that the code processing only once in a single row matrix A in each iteration of the outer loop. So only once the outer loop, that A will be executed only once. That is about the outer loop. And if we see the second loop here, that is j equals to 0, j less than m, j plus plus, iterates over the columns of matrix A here. Then the innermost k loop iterates here. The innermost k loops, that is for k equal to 0, k is less than n, k plus plus. This loop iterates over the elements of the row of the matrix B. So as you see from the columns of the matrix C to compute the dot product of the each element of the A. So this example shows the principle of locality, wherein the processor stores the data which in the memory locations which are near to each other. So in the same example of the principle of locality, we'll see how the memory is accessed. That is the matrix A element here. The matrix A elements are accessed sequentially in a memory as they are contiguous in the memory with the same row here. Whereas in the matrix B and the C elements are accessed sequentially within their respective rows and the columns. So this will tell how the memories are accessed in a program. So this is an example of the program written in the processor for the memory hierarchy design. So this exhibits the principle of locality. And in the same thing, from the same example, we can find out the cache performance. So since the access patterns exhibits a special locality, that is, it is likely to be benefit from the caching. So the repeat accesses to the same elements of the matrix B and C within the innermost loop may exploit the temporary locality. So potentially keeping these elements in the cache for the reuse. So whatever the data which is stored in the matrix B and C will be used for the future executions of the program. So that is why the cache memory increases the speed of the operation. So whereas the outer loop, that is I is less than equal to 1, okay, iterate only once, whereas the inner loops will be executed frequently. So this means the computation for only one row, that is A, is performed at one time, and which might limit the effectiveness of the cache perfecting strategy for the subsequent rows. So after seeing this, the principle of locality, so there's we'll discuss about the memory wall problem. So the phenomenon, it is a phenomenon. The memory wall problem is a phenomenon that occurs in the computer architecture when the processor speed outspaces the rate at which the data can be transferred to and from the memory system. So whenever the processor exceeds or will be unable to execute the things which are outside the processor speed spaces, and it don't has a memory, so then this problem will arise. As a result of this, the processor must wait for the data to be fetched from the memory, which slow down its performance and its limit speeds. So in this figure we can see because of this there is a difference in the performance of the memory of the processor and the DRAM. So as on the x-axis the number of years are taken from 1980 to 2010, and on the y-axis for the different processors the performance is calculated. That is, here 10 is number of executed the instructions executed, millions of instructions executed per second. So that is 10 millions of execution per second. So as you see from the graph here, from 1918 to the 2003, the widening gap performance is observed between the processor and the DRAM. So this is the processor memory. So the processor memory is increasing as the number of years are increasing, whereas the performance of the DRAM is being increasing slowly. So this is a memory wall problem which occurs when the processor speed and the processor don't have the enough memory to execute any instruction. That is, in the x-axis we have represented the number of times here, and on the y-axis so we have written the performance in terms of the measured in millions instructions per second. So for the same example, we can see the processor speed with compared to the DRAM here. So that the DRAM memory access speed is more gradual increase over the time, so signifying about the DRAM. So the processor is made of the SRAM, that is why it is faster, whereas the DRAM is the main memory is made with the help of the DRAM. So that is the memory wall problem, because in the processors are made of SRAM, which is faster compared to the main memory, which are made by the help of the DRAM. So we'll see what are the factors which are affecting the memory wall. That is the technology limitations, that is the physical limitations to how fast the DRAM can be made due to the factors like the signal propagation delays and refresh requirements. So now there is a huge gap between the DRAM speed processor and the DRAM memory and the processor speed. So this can be filled with the by avoiding these factors like the signal propagation delays and refresh other requirements. Then the cost consideration. So the high performance DRAM is more expensive to manufacture. So this can make it less economical to keep DRAM speed on pair with the rapidly increasing processor speeds. So what are the approaches of addressing this memory? Well, these are some of the approaches we can find. That is, computer architectures have focused on optimizing the memory hierarchies. That is how effectively we can design the memory hierarchy from top to the bottom of the hierarchy, and by utilizing the techniques like multi-level caching and exploiting it. So instead of using the cache in the only the one level of the memory, so we can use the cache at the different levels of the memory hierarchy design. Then we have to use reduce the locality of reference can be reduced. Then the alternative memory technologies can be used, such as 3D expert memory or the RAM technologies. So once we see the principle of locality in the memory wall problem, we'll see how the memory hierarchy is designed. So the top the hierarchy ranks various types of the computer memory, as you have seen in the previous videos. Also, we'll see here in detail. So the first level of the memory is the CPU registers in the computer. So that these CPU registers are used to store temporary data that the CPU is currently working on. So registers have very short access time, typically measured in the nanosecond. So even though so this will execute the instructions in the nanoseconds. So then this is the first level. Then the L1, that is the cache, that is level cache 1. So this memory, this diagram shows the different levels of hierarchy in the computer. So the CPU registers are made of the size of 1 KB and the speed is 300 PS. Then the next level of the cache is the L1 cache. So in the L1 cache, this is a very small and very fast type of the memory that exists between the CPU and the processor, CPU and the main memory. So it stores frequently accessed data from the main memory to reduce the number of times the CPU needs to access the slower main memory. So instead of each time the processor is the CPU is taking the data from the main memory, so from the L1 cache, the instructions, the data will be taken for the execution. So that is, we can say that the L1 cache is typically measured in tens of kilobytes. It's very fast. That is about 64 kbps. It is a speed and 1 nanosecond of access time. Then the next level is the L1 level here in the L2 level. That is compared to the L1 level here, it is slower, L2. So as we come from top to the bottom, the speed will reduce. So in the L2 cache, so the memory is designed in such a way that in the top L1 cache will be faster, then L2 is less faster than this one. Yeah, it's in terms of the speed, it is more L2 cache. That is 256 kbps and delays of 3 to 10 nanosecond. Then in the L3 cache, this is the largest and the slowest type of. So as we are coming from top to the bottom of the speed, the size of the memories, L1 caches are more, but the speed is slower. It is getting less slower. So as we are coming from top to the bottom of the these are the sizes of the register. So in the L3 cache, if you see, this is the largest and the slowest type of the cache memory. That is, L3 cache is typically measured in the megabytes. Then comes the main memory. So here the different caches can be used in different levels. That is L1, L2 and L3. So after the cache memories, then it comes the main memory. That is the primary memory of the computer system. It stores all the programs and the data that the CPU is currently using. So in the main memory is significantly slower than the cache memory because it will store all the programs and the data that the CPU is currently running. So it is obviously slower and its size is typically measured in gigabytes, actually main memory. And when the CPU needs the data that is not in the cache, so it reduces the CPU takes the data from the main memory. Then the next levels of memories are the secondary levels, that is the disk storage and other types of the memories which will have more capacities to store, but they're slower. So it's hard. Disk drives and solid state devices are much slower than the main memory. So in which the access times are in the range of millisecond. So here the memory hierarchy is design a strategy that balances the speed and the capacity. So according to requirements, the different levels of caches should be selected at the each level and the design of the main memory. So to achieve the better performance. So these are some of the examples of the secondary storage. So the next topic is the cache memory design. That is, we'll see some of the basic concepts of the cache memory. That is, the first one is the cache miss. So whenever the function of the cache is placed between the CPU and the main memory, so whenever processor is executing any task, so it takes the recently executed or the data from the cache. So cache misses happens when the data of the program is not found in the cache memory. Then if the processor is requesting something from the cache, if the cache is not having, so it is called as the cache miss. So the CPU incurs a penalty, that is extra clock cycle, to fetch the data from the memory in this case. Then the miss penalty is the number of clock cycle that takes to service a miss and retrieve from the data. So that is the time is calculated, and the miss rate. The miss rate is the percentage of memory access that results in a cache miss. Then the CPU time, and the total number of the CPU takes to complete the task. So which is measured and multiplied by the clock cycle in time, as you can see in this figure here. So the CPU time is calculated here, that is cache hit. So cache hit is whenever processor is asking any some data. So if the processor is able to give it, it is called as cache hit. That is a success. That the data is present and it is given to the processor of the CPU for the execution. So which is calculated as a product of the clock cycles into the clock cycle time. Then we have to remember the term called as memory stall cycle. So it's a formula that is calculates the number of clock cycles the CPU is stalled to catch the misses. So this memory stall cycles will find out the number of catch misses. So it considers the number of instruction catch misses, then the memory access per instructions, then the miss rate and the penalty. We'll see in the later section how to calculate these CPU time and memory stack cycles. Then the CPU time, the total CPU time or the cache miss is a factor, that is memory stall cycles into the computer CPU time when there are cache misses. So this is a hit scenario. This example shows a hit scenario here. So whenever the processor is asking some data, it is giving it, and the second case the data is not given, so again it is going in the loop. So you'll see some of the basic time, that what the definitions here, that is CPU time. So this refers to the total number of amount of time it takes for the CPU to complete one task. So then it is calculated by multiplying the number of CPU clock cycles by the clock cycle time. That is the total CPU. So CPU time is basically time which is required to execute one instruction. Then memory stack cycles represents the number of clock cycles that the CPU stalled while waiting for the time for the memory in terms of the cache miss. So whenever the data, whenever the cache is not able to give the data to the processor, so the time at which it is waiting is called as memory stall cycles. Then the miss penalty is the number of clock cycles to take the service cache misses and fetch the data. That is, after missing the cache, what is the time taken for that, plus the to fetch the data from the, so both the time should be will be calculated in the miss penalty. Then the miss rate. So this is the percentage of the memory access that accesses the results in the cache miss. So these are some definitions we have to remember. Then we will see how to calculate the cache performance calculation. That is, we'll see first how to calculate the CPU time. As we have seen in the previous slide, CPU time is the time required to execute one instruction, so which is calculated as the formula is like CPU clock cycles into the clock cycle time. Then the memory stall. So memory stall is the waiting period of the time, okay, at which the processor will wait because the CPU, the cache is not having the data to be given. So it has to take it from the main memory. So that total time is called as the CPU time. That is CPU clock cycles into the memory stall cycles into the clock cycle time. So the total time period will be calculated in this case. Then memory stall cycle separately is calculated as the number of misses into the number of penalty. Then the memory stall or the instruction cache is calculated with the instruction cycle time, then the miss instruction time and the penalty instruction. So then the total miss rate can be calculated with the instruction cycle time taken by the instruction to execute one instruction, then the miss rate instruction plus the penalty. So that extra time will be calculated. So now we'll see the perfect cache versus the memory stall. So the perfect cache in the sense, whenever the processor or the CPU requires any data, it will take it from the cache memory. So that is called the cache hit. That is the perfect cache. So then, whereas memory stall is the case wherein the cache miss is happening. So the cache is not having that data; it has to wait for the. It will take it from the main memory and it will do it. So we'll see this performance difference of the perfect cache versus this. So in the perfect cache case, the cache is ideal and can fulfill all memory access requirements. Whereas, so here the number of cache misses will be 0. So that no memory or the stack cycles can be. So the CPU time will be the speed will be more here. The CPU execution time will be more in case of the perfect cache. Like in case of the perfect stall, is a scenario wherein the caches will have the misses here. The formulas account these misses by factoring in the number of misses and the miss penalty. So resulting in an additional stall cycles and the CPU takes the extra time to execute such instructions. So by analyzing all these formulas, the computer architects can access the cache performance and ideally areas for the improvement and such reducing the miss rate. So when we are designing a cache memory, our main concern is to reduce the cache misses so that the CPU time will be more. So let us take an example on the same here. That is, assume that the CPI, clock per instructions, of a computer is 1. Then when all the memory accesses hit in the capacity, if the 30% of the instructions loads data, then there are 100. That is, miss penalty is 100 clock cycles. Then miss rate is 5%. Then how much is faster is the computer be able to? So we have to find out what is the speed of the CPU, or if memory access are hits, so what are the percentage of hits, or what is how much time is the faster the CPU is computing. So the total CPU time is calculated with the formula as you seen earlier. Clock cycle, CPU clock cycles into the clock total clock cycle of the time. So we'll see it one by one. This is a formula here. So the CPU time is calculated with the instruction cycle into 1 into the clock cycle time, memory access time instructions, miss rate into miss penalty. We'll see it one by one. So the memory, the CPU time is calculated as the memory access time, that is the time taken to execute the instruction into 1. We'll substitute the values. Then clock cycle time, memory access, and miss rate into miss penalty. So all these values will substitute, and now we have to find the clock cycle time and CPU time memory install is calculated with this formula. See, now we'll find out one by one. That is, instruction per cycle, IPC is calculated. It is a average of the CPI for the system. So it is calculated with this formula. That is, as we mentioned in the previous slide here. So the values are given 0.7 into 1. So if you substitute the values, so this accounts the CPI, that is clock per instructions, that is IPC. So this account the 70% of the instructions have CPI of 1 and 30% instructions are loads the CPI of the 1. Then how to calculate the memory stall cycles? So when a memory misses the cache, so the penalty of 100 cycles. The data is given. So for every instruction, 5% of chances of memory access miss are there. So resulting in the 100 cycle per miss. So we'll calculate this with the formula, that is 0.3 into the load store instructions into the 0.05, that is 0.5%. Then the value of 100 is given, is a miss penalty. So the total memory stall cycles are 1.5 cycles is the time which is it is the extra time taken for execution of the instruction. So now we can calculate the total CPU memory time. So the total CPU time for the example here is uh, uh, done with this formula, that is instructions into clock per instructions number of, then the clock cycle time and the memory stall cycle. So we have calculated the clock cycle time as well as this one. So we'll substitute the values of all this, and we have got instructions into 2.5 the clock cycle. So if we take one instruction cycle, so if you compare with the ideal case, there are for this the CPU time in the ideal case would be CPU time without the memory stalls. So this is a comparison. So it will obviously take the less time. So if you substitute, if you want to find out the speed of the CPU, so all the instructions where cache hits, and we can compare with the CPU times of both. So the speed will be calculated with the CPU time without the memory stalls divided by CPU time with the number of stalls. Then therefore the computer would approximately, if you substitute the values of clock cycles in this one, 2.5 times faster than the instructions were in the cache hits. So if we compare this example, we have compared the approximately 2.5 times faster if all the instructions were cached hits compared to the scenario of the examples in the memory stalls given. So if there are memory stalls are there, or the cache misses are there, so there are chances that the CPU will be executing, as the CPU will obviously take the more time for execution. Yeah, same times in the same formula we have substituted. So that's it in this presentation. So we have seen these are the references we have used. So these are the references we have used for preparing this video. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.